So let's continue our discussion here of different types of threats and attacks onto the network. And the next one we have is the type of reconnaissance attacks in which the hacker or the attacker is trying to gain information about the network in order to launch a further attack onto it. Now, these are also considered network mapping attacks, where basically someone outside the network, let's say on the internet, is running maybe a ping sweep or a port scan to try to figure out what are the actual end hosts and what type of services are they running in the network. Now, this is usually a precursor to some sort of exploit, maybe against a web server or a database server, or some sort of password attack, maybe a brute force attack or a dictionary attack against different types of devices in the network that are offering login prompts. Now, a perfect example of this, let's say that someone wants to try to gain access to your iOS routers. So the first thing that they would want to do is to send a bunch of different pings to random addresses in the topology. So this is what is known as the ping sweep or the ping scan. So we're just sending pings to random destinations. Next, we look at what are all the responses that we get back. So any host that responded, we now know that they are alive in the network. So that address is assigned. Now from the host that responded, now we're going to do a port scan. So with TCP, we're going to take common port values, let's say 23 for Telnet, 25 for SendMail, 80 for web, maybe 443 for SSL. And based on those, then we're going to send the TCP queries. So from the addresses that we found in the ping sweep, we send the port scan. Port scan gets to TCP port 23, which is for Telnet. So the attacker sends the TCP SYN, which is the first portion of the TCP three-way handshake. They get a SYN-ACK in response. The SYN-ACK is the response, that's the second portion of the handshake. The attacker now knows that someone is listening on port 23. As they go further and actually open the connection, they see that the data stream they receive in is a login prompt. So now they know that there's some system on the network there that is offering access through Telnet. So based on this, that we can further go into our access attack where we're trying to brute force the password, or maybe just try some common passwords like password, super user, root, that type of stuff to see if we can get access into the network. Another way we could do this would be with DNS queries. So if you are running public DNS, so if you have your own domain that is that's hosted, all you have to do is query your root DNS servers and ask which entries do you have actually registered. So let's say, for example, we have www.abc.com is our organization. And in addition to the www server that is public, we also have our SQL server registered. We have sql.abc.com. So even though maybe this is internal, we still have an entry for it. So normally requests don't come from the external network going to the SQL server. But someone queries the DNS server, says, give me all the records under abc.com. DNS server responds back and says there's www, but there's also sql.abc.com. So based on that, it's fairly obvious to the attacker what that particular service is running. So then maybe if we know vulnerabilities in that particular service, then we can launch a further attack on it. So the idea behind the reconnaissance attack is really that we're just trying to gather more information about the network. Now, in order to prevent these type of attacks, we need to know what is the methodology that the attacker is using to map the network in the first place. And a lot of this is going to come through the ICMP stack, the Internet Control Messaging Protocol. Now, normally when we think of ICMP, we think of ICMP ping, which is the echo and the echo reply. Now, we already talked about the Smurf attack that uses the ICMP echo and the amplification segment in order to get tons of echo replies to go back to the victim. But inside ICMP, there's also other applications, or what's known as ICMP type codes, that are used for different types of error reporting and information. So originally when ICMP was developed along with the IP stack, they weren't really thinking about security in mind. They were thinking more about open networks and to make sure that just everything worked together. So ICMP has a lot of little known applications that it could be used with. For example, the ICMP mask reply. Now ICMP mask reply, like an ICMP echo reply, is the response to the ICMP mask request. ICMP mask request says, I send you the mask request. I'm asking, I know your address already, okay, because I'm sending you the request in the first place. I know your IP address. I want to know what is the subnet mask that you have assigned to your interface. You reply back to me with the ICMP mask reply. You say my subnet mask is 255.255.255.0. So from an attacker's point of view, what does that help me know now about the network? I know your address, because let's say I did a ping sweep and I found your address. I now also know your subnet mask. I can now fine-tune my ping sweep or my port scan to target just the addresses that are on that individual subnet. So if the ICMP mask request and reply is enabled everywhere, just based on pings and this other type code, an attacker potentially would be able to map out the entire internal network. Another example would be the ICMP redirect. Now let's say that I send a ping that's going to the address 1.2.3.4. Now some router that receives this ping, they send a message back to me saying, don't use me to get to 1.2.3.4. You want to use this other guy. You want to use 5678. Okay, so a redirect means that if I receive an IP packet in and my route to get to the same destination is back out the same way the packet came in, normally I would respond with a redirect to the source saying, don't use me to get to that destination. Okay, think of it kind of how like Split Horizon works in RIP. Normally Split Horizon says you receive the routing update in. You're not going to send the routing update back out that same interface. A ICMP redirect is the same type of principle. You're telling the source, do not use me to get to the destination because I'm using this same interface to get there that the packet came in on. The problem with this is that ICMP redirect can be used to discover what the routing table looks like. And based on discovering the routing table, then I can then use that as a further mapping tool to figure out what else is going on in the network. Okay, also unreachable there, this is going to be the opposite of redirect. Let's say we have that same situation. I'm trying to reach the destination 1234. I send the packet out. The router gets it. They respond back to me with ICMP unreachable. They're saying, I do not know how to get to 1.2.3.4. So what does this tell me? If they don't know how to get there, it means it's not in their routing table. So the unreachable mapping attack is looking at the opposite of what is unreachable. So the opposite of what is unreachable should be reachable. So if I send pings to every possible destination and I get rid of all of the ones that unreachable came back in, that means that whoever I sent the packet towards, I now know exactly what their routing table looks like. Or at least I know that they have those entries in the routing table. So when you start to combine these together, you'll find that the attacker can get a pretty accurate picture of the network in a very, very short period of time. And unless these services are explicitly disabled, a lot of the times in hosts, they are on by default. Okay, the proxy ARP, we'll talk about that a little bit later when we get into layer 2 type of attacks. But basically that would be using the address resolution protocol, that layer 2 MAC address to layer 3 IP address mapping. We can use that to discover what the routing table looks like for devices on the segment. Okay, another protocol here would be CDP, the Cisco Discovery Protocol. By default for all Cisco iOS devices, all Cisco Catalyst switches, and a bunch of other devices like Cisco phones, some of the access points that are running versions of Cisco iOS, they're basically advertising a lot of information about their system. They're advertising not only what is my IP address, but details about the operating system down to the individual version. So let's say that I'm a service provider and I'm advertising down to my customers on my DSL links. I'm advertising the iOS version of what the border router is. What could be the potential problem with that? If the attacker looks up that individual version and looks at the release notes and looks for any security vulnerabilities, they know exactly how to form the attack against that particular device. So most of the time, CDP you would not want to run in the network. You should, as a network designer, already know what your topology looks like. There's very limited applications of what you would want to use CDP for. Today's networks, pretty much the only thing would be related to your voice over IP phones. That there's a portion of the provisioning with the layer 2 switches, how they detect the Cisco phones by using CDP. But from the routers themselves, it's probably not a good idea to run that. Okay, so a lot of the issues here with the reconnaissance attacks where they're trying to get more information is to figure out what are the services that I do not need to run on the router. So think about this like in Windows. You go to your task manager and you see that there's 10,000 processes running. What really are all these processes in the background? Do I need all of these? Same thing with the iOS. But the problem is, it's much harder to sort through the show processes output on the iOS unless you already know exactly what individual process names relate to. And it's actually very, very hard to figure that out. You would have to know a lot of low-level information about the iOS in order to see that. Another way to mitigate this would be with the intrusion prevention systems. We'll see later when we configure the Cisco iOS IPS, there are some signatures that relate to these type of mapping attacks. So if someone is doing a ping sweep or they're doing a port scan, a lot of times the intrusion prevention system will figure this out. Then you could tell it what to do based on that. You want it to just send me a message through syslog logging, or do you want to go to the border router and automatically configure an access list to deny them entry into the network? So that would be a reactive mitigation for the port scanning, where the proactive mitigation would be to disable the unneeded services in the first place. Okay, next we have attacks against the control plane of the network itself. As I mentioned, the control plane means the protocols that are running behind the scenes to do the actual management of the network, or the basic low-level functions of the network. So like our routing protocols, maybe the network time protocol, the simple network management protocol, SNMP, be considered part of the control plane. Usually attacks against control plane are going to be related to denial of service. So if I can trick you into resetting your BGP sessions or trick you into dropping your OSPF neighbors, then that just means that the router cannot forward packets. So it's going to be a network denial of service attack as opposed to like the DOS attack using the Smurf attack or using TCP/SYN. Okay, so it's against the network itself, against the routers itself. Now, the reason that the network would be vulnerable to this in the first place is that you have a lax security policy for those control plane protocols. So if you're running OSPF in the network, you should always run OSPF authentication. If you're running BGP in the network, likewise, always run BGP authentication. Okay, there's some other additional security mechanisms that are built into those protocols where I could say with EIGRP, for example, I don't want to accept updates from everyone. I want to accept it just from this neighbor router on the segment, and I already know their IP address. So when you get into these type of details, it gets into that point where how does the likelihood of the attack, which is going to be the risk factor, relate to how manageable your solution becomes? Because you can get very, very secure down to the low level to protect the control plane, where we're doing things like the unicast updates would be to say I only want routing updates from this particular neighbor. I could also say configure an access control list to only allow EIGRP from this particular neighbor. I could even go further than that and say from a layer 2 perspective, let's say I'm running Ethernet, I only want this particular MAC address to send me packets. So there's a lot of ways you can get into real detail and really low-level control of this. But then it gets to be an issue, the management of the network, when you compare the risk factor of the attack. So some of these are feasible, some of them are not. Definitely routing authentication, you would always want to run that. Okay, third one down, clear text telnet and SNMP passwords. Nowadays, there's really no excuse for doing this in the network. A telnet should never be used for a management technique. Neither should SNMP version 1 or SNMP version 2. Reason why is that they send their passwords in clear text. So anyone who were to receive that packet, if they're running a sniffing application, they'll simply see in the payload of the TCP data what the actual password is. For SNMP, this is called the SNMP community string. So when we get to the secure management, tomorrow we'll talk about things like SSH that you would use to replace Telnet, SNMP version 3, which does encryption and authentication. You would want to use that to replace the older versions. Then another one, which is kind of an obscure issue, but it definitely is important, is the time of the network. That comes from the Network Time Protocol, NTP. And the reason that this is an important issue is that time is used to make sure that you are keeping accurate logs in the network. So let's say, worst case scenario, someone does get into your network and they make some changes on your database server. They download credit card information from your customers. Now, if this occurs, you're going to want to give some sort of evidence to the law enforcement for them to try to do a further investigation. So you would want to know exactly when did the attack occur. So if the attacker comes in and they change the time, then you really don't exactly know when this occurred or what type of stuff that they changed in the network. So one way to do this would be to make sure that all devices have accurate time, and you would want to make sure to authenticate that time information from the network time protocol. A network time, like for example in Windows, if you open up your clock on Windows and you go to internet time, it says I'm going to synchronize to time.windows.com. That's exactly what that is referring to, is the network time protocol. So most of the time this runs in just a clear text format with no authentication, but to make sure that the control plane is really secure, you would want to add that extra level of authentication there for NTP. Okay, next we have the denial of service or distributed denial of service attacks. Talked about this a little bit already with IP spoofing and the Smurf or the Fraggle attack. Basically, this is an attack on the availability of the network. So either the network itself, the bandwidth of the links, maybe the CPU utilization of the routers, or the applications themselves. So the CPU utilization of the web servers or the database servers. We're trying to send so many requests that the service simply becomes unusable. Now, in today's networks, Smurf and Fraggle, they're very, very easily mitigated. We'll talk about that on the next slide. So most of the time, Smurf and Fraggle are out unless you have a very lax security policy and you don't understand what the attacks are in the first place. Okay, the fourth one there, the SYN flooding attack, sometimes this is a little bit harder to fix, harder to mitigate, because sometimes it's hard to figure out, are these legitimate requests that are going to your services, or is it someone trying to overwhelm the network? And you get into what's sometimes referred to as the dig effect. If anybody is familiar with the site dig.com, a lot of times you'll see a story become popular on this news site Dig, and so many users go to visit the web browser at once that basically the web server just can't handle the request and it dies. So there are cases where SYN flooding is legitimate, that you just have tons of traffic going to your applications. There's other times when SYN flooding is not legitimate. And we'll talk about that. We'll talk about that tomorrow, I believe. Yes, tomorrow when we get to the firewall feature set, I'll get into that in more detail. It's basically an attack on the three-way handshake of TCP. So I ask the web server, I say I want to open a session. They reply to me and say, okay, let's open the session. I never reply with the third step of the handshake, and now the server has what is known as a half-open session or an embryonic connection. Okay, the issue we run into, if we look at the next slide here, is that the TCP stack itself has a finite limit of connections that it can have. And that would depend on the operating system and whatever application you're running. So let's say you're running an Apache web server. There's some hard limit, albeit it may be hundreds or thousands or tens of thousands of connections. There's still going to be some limit to where Apache says, I cannot receive any more requests. And once you hit that hard limit, that's where you get to the denial of service, is that any new legitimate connections coming in, the server cannot respond to them. So there's some ways to fix this that are based on the servers themselves. So strategies today with people like Yahoo or Google or a lot of very large websites, let's say like YouTube, it's simply not possible to bring them down based on a TCP SYN attack because their servers are so large and so distributed over the world. So you may see that I could bring down the, let's say, Chicago mirror of Yahoo if I had enough hosts attacking it, but overall you're not going to be able to bring them down because there's simply so many raw server resources that they're throwing at the problem. Okay, the other way to fix this is going to be based on firewalls. So you can have the router or the firewall act as basically a proxy in the middle between the client and the web server or whatever TCP service they're running. So the firewall acts as a proxy and it monitors how many sessions are trying to be open. And based on thresholds that we configure, we'll say that if more than 1,000 connections try to start per second, then I'm going to start shutting them down. Okay, but we'll get to that in more detail when we look at the iOS firewall feature set. Okay, the second one with the Smurf attack or the Fraggle attack, the key in stopping that is to stop the amplification. And remember when we looked at the diagram there, we had the attacker spoofing the source address. Okay, so the attacker takes the victim's address, puts it as the source field. The destination field is a broadcast address. Okay, it's a broadcast address for an individual subnet that is also known as the directed broadcast address. So if we can stop the router from using the directed broadcast address, then it defeats the whole attack. It's a very simple implementation. It's simply one command on the router's interface. It's no IP directed broadcast. And basically, all interfaces should have this by default on all routers. Okay, there's really no reason that you need to deliver a directed broadcast for any legitimate application. Okay, the other issue to defeat spoofing attacks that are part of denial of service is as the packets enter the network, we would want to check where they are coming from. Now, we'll get to this again in more detail tomorrow when we talk about access lists. But let's say, for example, that my public addresses of my network are 100.0.0.0. So I registered those addresses with Aaron, and they assigned me the whole block 100.0.0.0. This is my whole public address space. Now, when packets are being received from the internet by me, so outside hosts are sending traffic in, if my addresses in my network are 100, it should make logical sense that no one is sending me traffic from the 100 space. Okay, so again, if my internal network is 100, there should be no one on the internet that is using 100 as their source. And this is basically what the logic of the RFC 2827 filter does. It's also called the bogon filter. Bogon list is basically a list of addresses that are not valid. Also the same logic that goes behind the unicast reversed path forwarding feature. Okay, basically all of these three techniques, what they're saying is that when packets come in from the internet, look at the source. If the source address is not valid, then just get rid of the packet. So this defeats the vast majority of spoofing attacks, because usually spoofing attacks are just for the point of blanket denial of service. Okay, but again, we'll get into more details about specifically how we prevent that when we look at the access lists tomorrow. Okay, next we have attacks on the access of the network. So this would be the attackers trying to guess the passwords of the web server admin interface or the routers themselves. A lot of this is going to have to do with just brute force or possibly dictionary attacks, where, as I mentioned before, common technique is the attacker does the ping sweep. Now they know who are the active hosts. They do a basic port scan to figure out, are they listening at this individual port? Okay, so now the attacker knows the hosts. It knows who's listening for telnet connections. Now they try telnetting in over and over and over, trying random passwords that would be brute force, or trying well-known passwords that would be a dictionary attack. Okay, other issues with this go down to the actual application level. So if somehow one of your users internally gets tricked into downloading a Trojan horse that installs a keylogger, every time that user is on their end host, the attacker can take whatever passwords they want, whether it's related to the network itself or whether it's related to their applications like financial data, etc. Okay, so those type of access attacks, a lot of the times they don't relate directly to the network. It's more of an end host security type issue where you would want to make sure you're running some sort of security suite, whether we call that network admission control or we call that host-based intrusion prevention systems. We want to make sure that those type of illegitimate applications don't end up on the end hosts. Okay, redirection, layer 3 man in the middle. We'll talk about that more when we get to our layer 2 attacks. But to stop these, a lot of the times it can be as simple as defining a very strict password policy. So if the users in the network are using 3-character passwords, it's not going to take very long for an attacker to run brute force against that. But if we say your passwords have to be 10 characters, be uppercase, lowercase, numbers, and symbols, then it's going to take them a considerable larger amount of time. A lot of the times you'll find out that the attacker will just move on to an easier system. Another possible reason for this would be clear text passwords in the applications that we're using. So if we have sensitive data that's going over web-based applications, don't run that as clear text web. Don't run it at port 80, run it at port 443 and use SSL. So then even if there is some sort of sniffing attack in the internet, then it's going to be encrypted inside the SSL payload. Okay, the other one, as I mentioned, would be the host-based intrusion prevention system. Another one we'll look at here today is the AAA service, the authentication, authorization, and accounting. Okay, not AAA for your car, this is AAA for the network. So authentication, authorization, and accounting. This is going to be used to make it easier to enforce a password policy onto the network as a whole. It's a management technique for your passwords in the network. Okay, last one we have here is the attacks against the applications themselves. So these would be things like worms or viruses, Trojans that are coming from the internet. Mitigation against this, sometimes this could be as simple as educating the employees not to open email attachments that are .bat files or macros, that type of stuff. It could also be going as far as running some sort of comprehensive security suite. So something like Symantec or McAfee, whatever, tons of vendors out there that offer these type of products. There's also a way to have the hosts interact with the network, which is starting to become a very hot topic nowadays, that is called either network access control or network admission control. So Cisco calls it network admission control. Some other vendors call it network access control. Basically means that my PC, if I wanted to log into the network, first thing it has to do is to ask the network, do I have the proper software patches installed in order to get onto the network? So the PC boots up, it gets an address through DHCP, it sends a request to the AAA server, it asks the AAA server, or it tells the AAA server, this is my service pack of Windows. This is my virus database date. Then if the AAA server responds and says, you need to update to the newer Windows Service Pack or the newer Windows security patch, or you need to update your virus definitions, you can force that host to do that updating before they actually get access to the network. So it's kind of an automated way of enforcing the policy of making sure that everything is up to date. Because a lot of times when the user gets that pop-up box that says, Windows update needs to run or your virus scan needs to run, they don't always agree to do it, because it does take some time out of the day to sit there and run the updates, reboot, etc. But that's what network admission control can try to enforce. Now, as a whole, all of these technologies that we talked about so far all fit into what Cisco defines with their marketing term, the Cisco Self-Defending Network, or the SDN. Okay, so from Cisco's definition, it says network-based approach to protecting the network devices, endpoints, and information traveling across the network. Opposite of what they call a point solution, where they're describing a point solution as a security device that is standalone. So if you buy a firewall from some third-party vendor, they're saying, well, that firewall doesn't interact with the IPS, doesn't interact with your host-based intrusion prevention, your network admission control, so it's not really an overall security solution. So I'm not going to spend a lot of time on this today because it's more of a marketing term referring to what Cisco's product line is. You can get more information about this at cisco.com/go/SDN. And you can see the 3 points that they describe it. It says it's integrated, adaptive, and collaborative. So integrated, in this case, they mean that security is running on your routers. Your routers are running ACLs, they're running firewalls, they're running intrusion prevention. It's also on the layer 2 switches because we're preventing layer 2 attacks onto the network. It's also on the endpoint because we're running something like the Cisco Trust Agent that runs along with the network admission control solution. And then it's in the server applications themselves. For example, like the Iron Port that's running the spam prevention, that type of stuff. Same with the ASA. ASA can run antivirus, anti-spyware, all sorts of application level filtering that it can get into. So the idea behind this is just that all the portions of the network are working together in order to provide the overall security suite. So I would, at least before going to the exam, I would recommend to look at that link there for the self-defending network and at least read some of the PDFs of their marketing explanation, because sometimes you will find some of these Cisco exams do get into some of the marketing terms behind the technologies.